So welcome everyone, and my name is Johan Frenji, and I'm the head of the MIT Plasma Science and Fusion Center's HEDP division. And it's my great pleasure today to introduce to you graduate student Patrick Adrian and postdoc Neil Kabadi. And they will give a talk today with the title Recent Exciting Fusion Results in ICF, and how the MIT Plasma Science and Fusion Center contributed to this effort. And a little bit about these two. Patrick comes from Chicago, Illinois. He got his undergraduate degree from University of Iowa in 2017. He worked at Los Alamos as a summer student in 2017, and he started his graduate studies in the fall of 2017. He is also a DOE SSGF fellow since 2019. Neil comes from North Carolina. He got his undergraduate degree in both physics and mechanical engineering from North Carolina State University in 2015. And as a undergraduate student, he did research on computational neutrino transport and also plasma discharges. And he finished his PhD in February this year in plasma physics, and is currently postdoc in the HEDP division here at the Plasma Science Fusion Center, while he's looking for future opportunities here right now. And with that, welcome everyone. Patrick and Neil, it's all yours.
Okay, thanks. So let me just bring up my slides. All right, everyone can see that all right?
Yep, we can see that.
Awesome. Okay, so yeah, welcome everyone and thanks for coming. So today we'll be discussing some recent exciting fusion results in ICF and discuss how our group and more broadly the MIT-PSFC contributed. So on the title slide here, I kind of have the number of DT neutrons from a specific ICF fusion experiment that we've been studying for a while now. And what you can see is kind of the exponential growth in how many neutrons we've been able to make from this specific ICF experiment. And what's cool about this plot is that all of this data is from an MIT diagnostic, which we'll discuss, that measures how many neutrons we can make with fusion. And that was installed really early, well, basically at the beginning of when this experiment started. And we'll discuss through this talk some exciting experiments that happened more recently in the past year to the right on this plot. But first, to get there, here's kind of the outline of this talk. First, I'll give an introduction to fusion. What is it and why are we studying it? Then Neil will give an introduction to inertial confinement fusion. What are ICF implosions? How do they work? And what are some of the performance metrics by which we rate how we're doing in producing fusion? And then I'll come back and give details some recent major progress that has been made in ICF, and we'll detail a period from roughly 2014 to 2019. And then we'll discuss an implosion design that has been performing incredibly well. And we'll discuss, as some of you might have heard in the news, a record-setting experiment in this field that happened in August of last year. And then we'll circle back, and Neil and I will both discuss how here at the MIT, our group has been developing and using diagnostics to support this research all across the country, across multiple labs, and hopefully that will give a good overview of the field as a whole. Okay, so let's start first with the introduction to fusion. So nuclear fusion is the process of combining light elements to produce heavier ones, and this reaction can be used to produce energy. So elements below whose atomic number are below iron can produce net energy by rearranging their nucleons. And the way this happens is if you were to go and physically measure, let's say a deuterium and tritium reaction, it will produce a neutron and a helium atom. If you were to physically measure the masses after that nuclear reaction, the neutron and helium would be lighter and there would be a mass deficit. We know from Albert Einstein that, well, energy and mass are kind of are equivalent. And so what happens is by rearranging the nucleons of these atoms, we've liberated some energy. We've taken them into a more tightly bound state and released energy that way. And that energy goes into the kinetic energy of the products. The helium and the neutron fly out of this reaction with very fast speeds relative to what the deuterium and tritium came in with. So already I've kind of biased this discussion of fusion to deuterium and tritium. So why is that? Well, it turns out if you were to go and study the light elements, what is the reaction that has the highest probability of happening for a given, let's say, temperature? It turns out that deuterium and tritium have the highest reactivity or cross-section. So they have the highest probability of fusing. So that is why most fusion experiments here on Earth pursue deuterium and tritium fusion. It's simply the most probable reaction to happen, and it gives us the best opportunity to make the most reactions as possible. And so the ultimate motivation of fusion research is, well, if you have a reaction that produces net energy, how can you get it to efficiently boil water is the main question. And the reason you want to boil water is because we know how to use steam to spin a turbine. And if we can spin a turbine, we can hook it up to a generator and turn mechanical energy into electrical energy we use to charge our phones and, have a society. And clearly what we're researching now is how to make the most amount of energy for a given input to do this. And the motivation is, of course, clean energy. A city requires tons of electricity, about 1,000 megawatts for a modest major city. And if you were to just burn coal, you would have to burn about 80 million pounds of it, or about 80 railroad cars a day. And that emits a ton of, well, let's say 61 million pounds of greenhouse gases. Whereas a DT fusion plant with the deuterium and tritium reaction, in terms of like consumable resources, would only burn about 3 like water bottles a day. And that's kind of one of the main reasons to look at fusion as a way to clean, as a source of clean energy. And so we can look for inspiration in the universe, and one of them is stars. And stars like our sun produce energy via fusion reactions. So we know there's a way to confine hot plasmas, but it's done by gravity. And gravitational confinement is pretty weak, and you need a ton of mass. And that's why our star is so large, about 800,000 miles in diameter. And it produces a lot of energy. And so the question is, how do we scale this down into the lab? And there are 2 leading strategies for confining really, really hot plasmas here on Earth. One is inertial confinement fusion. And this is a picture of what we'll discuss is a target chamber in one of these experiments. And there's a person for scale here, just to give you all scale. And there's another concept called magnetic confinement fusion. Again, person for scale. And this is actually the Alcator CMOD, which is another MIT experiment in fusion. But for this talk, we'll focus on inertial confinement fusion. And so with that, I'll turn it over to Neil. That's kind of the introduction to what is fusion. And now we'll go into specifically how ICF works.
Yeah, thanks, Patrick. Yeah, so I'll talk about inertial confinement fusion, or as we'll abbreviate it, ICF. I'll start by talking about ICF implosions and kind of how those proceed. And then I'll talk about some implosion metrics that we use to determine, after we've done an implosion, well, how well did it perform at, our goal of producing fusion. Right, so you can go to the next slide, Patrick. So I'll go through a series of cartoon steps here to kind of show how an ICF implosion proceeds. So on the left, I'm showing here our initial capsule, which is about 1 to 2 millimeters in diameter, so quite small to start out with, and we're going to try to make it even smaller. And the capsule is filled with a DT or deuterium tritium gas or vapor, and surrounding that is a DT ice layer, which will eventually become the bulk of our fusion fuel, as this dense DT ice contains quite a lot of the deuterium and tritium we want to fuse. On the right, I'm showing a radius versus time plot of the kind of trajectory that this capsule will go through. And in the little green shaded regions will be kind of the phase that I'm describing on the left. So right now we're right at the beginning. Not much is happening, and we're going to start radiating the outer surface of this capsule, primarily through a laser drive. When that happens, that outer surface gets to be very hot and it blows off, or ablates as we would call it. And this outer material carries with it quite a bit of momentum. And so by conservation of momentum, the material that's left behind will implode inward. And in this process, we launch multiple strong shocks through that ice fuel layer. These shocks can coalesce on the inner surface. And then we can go to the next one. Yep, those shocks will coalesce near the inner surface, and they propagate through that DT vapor, what was initially the DT gas, which has now at this point turned into a plasma. When that shock rebounds off the center, you get a central region that's very hot and a little bit underdense still. We start getting some initial fusion reactions where our deuterium and tritium are producing an alpha, which is a helium ion, and neutrons. And our goal is that by this point, we've gotten compressed far enough that alpha doesn't leave our hotspot, but actually stays nearby and deposits more energy, therefore raising the temperature. And then we go to the next slide, and we see that if we can achieve this and we're near peak compression, those alphas will heat up that initial DT ice to the point that it now reaches fusion conditions, and we get a larger mass of fusion producing reactions. And this is what we would call ignition. So we've essentially caused the DT reaction to propagate itself by producing excess energy that's then confined by this density. And so we would get a substantial amount of fusion reactions and hopefully some net energy out relative to what we put in. So this whole thing proceeds in about 10 to 20 nanoseconds. Our hotspot, that central region that initiates our reactions, needs to be quite hot, about 5 kilo electron volts or 100 million Kelvin. Our densities need to be quite high, above a typical density of solid material in this hotspot. Now, if we look at the dense fuel, well, it's going to be heated by the fusion reactions rather than our implosion. So it can actually be an order of magnitude lower in temperature at only 500 EV, but we want it to have a lot of material to fuse. So it's an order of magnitude higher in density. So the idea is to use this hotspot, kind of like a spark plug in your car, to get everything nice and heated up so that that energy can then propagate into the dense fuel and burn the majority of our material by fusion reactions. So that's how an ICF implosion proceeds. But how do we really drive it? And there's kind of two main ideas that we'll just go through quickly here. One is a laser direct drive approach, in which a laser is used to irradiate the outside of a sphere symmetrically. This laser directly deposits its energy into your capsule, causing that ablation and implosion. One of the major issues with direct drive is that laser beams, although this has actually gotten a lot better with newer technologies, laser beams can have non-uniformities in their kind of emission profile. And so these non-uniformities will actually seed non-uniformities in the surface of your implosion. And as you compress the implosion, this can cause breakup of the shell and loss of confinement. So it's important to maintain symmetry on the small scales, which can be hard to do with a direct drive approach. Another approach is indirect drive. In an indirect drive approach, rather than directly shooting the capsule, our beams are actually going into a gold cylinder, or what we would call in ICF a Hall-ROM, as another kind of jargon term. But what this Hall-ROM is really doing is kind of acting as an oven. So we're putting all of our laser beams into this Hall-ROM, hitting the walls. The whole thing is heating up, and then the Hall-ROM re-emits X-ray radiation. And these X-rays then are what drive our capsule. And the reason that we use this approach is that the indirect drive in this way is much more uniform. So kind of like the analogy of an oven, if you have some sort of a hot burner and you use it to fry something, that burner could have, hot spots here and there and cause non-uniformities in whatever you're trying to cook. But if you put that in an oven, then the oven, even if you heat it with an element that might not be uniform, will then still kind of uniformly heat your item that you're trying to bake in there. So that's the idea with the Hall-ROM, but the problem with that is you have to heat an entire oven just to cook your small capsule that's in the middle. So this can cost efficiency relative to a direct drive approach, but can give higher uniformity in the drive. So for after we do one of these implosions, how do we quantify how well we did? Well, two of the most important metrics are the areal density, or rho R, as we'll call it sometimes. And we call it that simply because it's the product of the total mass density and the radius. And so this gives a good measurement of how much material a fusion product from the center of an implosion has to traverse in order to get out. It has to go through this much density, and it has to traverse this much distance through that material. And so it gives us an idea of how well we can deposit those alphas into our hotspot and therefore propagate a fusion burn. The other important property here is ion temperature, or temperature of that hotspot plasma. This temperature is very important because we need to be at a high enough temperature to produce substantial numbers of fusion reactions, which don't occur at low temperatures. And so in the plot here, I'm showing the temperature of the that hotspot material on the vertical axis and the areal density on the horizontal axis. And we can see this black solid contour in the upper right corner, which shows the minimum requirement for ignition. So if you went through kind of some textbook assumptions of how things go and tried to figure out where you need to be to achieve an igniting implosion, we would find that you need to be to the upper right of this contour at the very least. You might need to be a little bit further beyond it to really have a real life implosion, but this is kind of where we need to be at bare minimum. And if you're kind of to the left of this curve and you don't have quite enough areal density, then you can lose to conduction, where energy is leaving your implosion via conduction faster than your fusion reactions are depositing energy. And if you have too low in temperature, then you can be actually producing less fusion reactions than you're losing to X-ray radiation from your hotspot. So those are kind of the two main loss mechanisms that we're fighting while we're doing these implosions. Another important metric is the convergence of the implosion. So how much we started out with, a 1 to 2 millimeter capsule, and we implode it and it shrinks down, but exactly how much does it shrink? And this is important because this convergence is how we achieve high areal density. So if you click to the next animation, we see that if we just say that we have to conserve mass, like we're not removing material from our central hotspot because it's well confined within our shell, then the final areal density, the ratio of the final areal density to initial is related to the ratio of the initial and final radii. And so if we go through the numbers, we find that we need to compress this thing by something of order a factor of 50 or so in order to get to the areal densities needed. for an ignited fusion implosion. And with that, I'll turn it back over to Patrick, who will talk about some recent major progress in ICF.
All right. So ICF has been studied since around the 1970s, but really the story picks up with the construction of the National Ignition Facility, and it's the leading ICF facility with 192 laser beams and a total energy of about 2 megajoules. And to the left here, a picture of what you're seeing is actually the NIF target chamber. So inside this target chamber was where we would do the fusion experiments, and you can see all the laser portholes and different diagnostic ports that give you access to what's happening inside the target chamber. It's about 10 meters in diameter, and this is a picture in around 1999 when it was being hoisted by this giant crane, which apparently there's a story behind this crane. It was actually shipped in from the DOE from the Nevada test site in Nevada into Livermore, California, just to hoist this target chamber. Interesting. And so that was in 1999. And NIF's footprint at the lab is about 3 football fields in size. And most of that footprint is actually taken up by just the capacitor banks and beam lines of the laser. Because to generate 2 megajoules of energy, you need a ton of storage and also just space to condition the laser beams that will eventually be shot into the target chamber via the different glass ports. So NIF probably finished construction around, I can't remember the exact dates, but around 2004. And then it was a bunch of conditioning the facility to, shoot what targets as Neil described. And so we finally got to that milestone, I would say, in around 2011, where the first cryogenically cooled deuterium tritium experiments. And so these were the first, these are serious attempts at ignition in the laboratory. And they didn't perform as well as we hoped. So the first era of shots, roughly from 2011 to 2013, on the National Ignition Facility had serious problems with keeping the shell stable. As Neil mentioned, you have to compress the capsule by, let's say, around 50 times its initial radius. And one of the ways you can think about this is if you were to take a balloon, kind of put your hands around it and try and compress it, it's really hard to keep the balloon not from escaping your fingers. And, just even compressing it by a factor of 2 is incredibly difficult. And so we ran into stability issues of keeping the dense shell intact as it was imploding inwards. So on the plot here is essentially fusion yield in kilojoules as a function of year. And here's a little it's not a cartoon, it is a cartoon, but it's representative of a simulation that was done of these implosions. And as you can see, they're not very spherically symmetric, and there's a bunch of swirling motion of the fuel as it's supposed to be assembled. That's detrimental to the ICF performance. So correspondingly, these experiments, if we go back to the familiar temperature versus areal density space, these experiments were unfortunately in the wrong corner of this plot. Of course, to the right is where we say we have a burning plasma or plasma that's dominated by alpha heating. These were to the bottom left of the plot. So they had modest temperatures and modest areal densities, but they weren't near the ignition threshold. So obviously we had to change something with the design, and the performance was improved by dramatically changing the laser pulse shape to maintain shell stability. So what we did was essentially backed off on how hard we were driving the shell inward to make it more stable. hydrodynamically. And so you can see in this temperature versus rho R space, what we did was essentially we relaxed the requirement on the rho R, and we were able to increase the temperature by more efficiently converting the shell kinetic energy into the internal energy of the hotspot. And that was able to give us more fusion by raising the temperature. And roughly this happened in the time from 2013 to 2016, let's say roughly speaking. And then finally, well, not finally, but the next step was in further improvements in the drive asymmetry and efficiency. And we'll discuss this a little bit in the next slides, but there are essentially what we did was to make the implosions much more spherically symmetric by playing with different parameters of the Hull realm physics. As Neil just mentioned, that's that gold can that we use to bake these capsules. And what that enabled us to do was to increase the rho R and while maintaining that high temperature that was desirable. And that got us very, very close to the burning plasma regime. And so around 2019, we were near the burning plasma regime, and we pursued implosion designs that could couple even more energy to the capsule. So we were right on the threshold, and we said, well, how, we just need a little bit more energy. We just need to, we need to cut some corners somewhere to just get even more energy on this capsule to push us over the edge. And that's where this concept, the high yield big radius implosion design or hybrid design, came into effect. So most of the implosions I discussed in that chart were high yield baseline targets. And so around 2019, we started to research into what we call, this kind of a jargony term, but the hybrid E design. And the key design changes were bigger capsules, as you can kind of see from this relative size. It's kind of hard to see, but we decreased the size of the hull realm, and we used smaller laser entrance holes. So why is this helpful? So in Neil's metaphor, he said the hull realm is essentially an oven. So if you make the oven smaller, you have to heat less of it. If you make the capsule bigger, well, you just have more more things to cook in some sense. And then by making the laser entrance holes smaller, we essentially can decrease the open ends of the bottle. And so that means we can just keep the heat that's in the hull realm in there for a little bit longer. And all of these effects were to increase the amount of X-rays that the hull realm generated, make it last longer, and increase essentially the capsule surface area to the surface area of the hull realm or the oven. And this pushed us to higher temperatures and higher areal densities. At the same time, of course, we had the hull realm design, but there was also actually target metrology that needed to be addressed. And so we needed to improve target quality. And the way we did this was pursuing material science and target fabrication research to decrease the amount of engineering features with seed instability. So the targets for this experiment, actually what holds the deuterium and tritium is actually a diamond capsule. I'm kind of pictured here. And what you can do is you can take radiographs or different images of the shell, and you can see defects, or there's engineering features like the fill tube, this is a tube that essentially pumps deuterium and tritium inside the capsule. And roughly speaking, these different features can be anywhere from 2 to 10 microns in size, and they have very detrimental effects into the implosion performance. As we compress the shell inward, this defect can grow and seed instabilities, which essentially puncture our confinement, and we lose confinement because of these effects. So those are the two areas of research that kind of led to what happened on August 8th. So there was a change in the hull rum design, and then there was a concerted effort to improve the target quality of these experiments. And what happened on August 8th, the National Ignition Facility achieved 1.3 megajoules of fusion energy. So this should be compared to the 2 megajoules of laser energy that the laser was fired with. And it generated at around 6 times 10 to the 17 neutrons using this new design. So to put it into context, here's the total neutron yields as a function of hotspot internal energy. So as you can see, kind of to the right or the left, excuse me, left of this plot is kind of from 2012 to 2021, all the experiments we've discussed before. And on August 8th, this experiment achieved substantially higher neutron yields and correspondingly higher hotspot internal energy. This is how much energy essentially the hotspot possessed to produce this fusion yield. And these results are still under intense review. There are no published papers for it yet, but by most indications, these shots achieved ignition in the laboratory for the first time. And I'll cite many presentations that were given about this experiment by at the American Physical Society Division of Plasma Physics meeting. And so with that, we'll now transition with that exciting, progress that we made to discuss some of the diagnostics that I, Neil, and many people from our group have developed and used to understand these systems and to support this achievement. So here at MIT, the high energy density physics group develops advanced diagnostics to assess ICF performance by measuring key performance parameters. So circling back to our fundamental discussion of how do we rate how well we did in ICF, we'll focus in on 3 diagnostics here at MIT that we've developed. One is for areal density diagnostic, and this is run at both the National Ignition Facility and the University of Rochester Omega Laser Facility. These are the 2 kind of main ICF facilities in the US. Neil will discuss a temperature diagnostic that both he and I and a bunch of other people have been building and researching at the Omega Laser Facility. And then I'll discuss some X-ray imaging diagnostics that I've helped develop and how we probe the size and shape of an implosion. And that's run both at the NIF and at University of Rochester. So first, let me just discuss how we diagnose areal density. So this is the fundamental performance metric on how well are we confining our plasma, how much density do we have, and how big is the plasma. And the way we measure this is through measurements of scattered neutrons. And the way to think about this is if you have your hotspot surrounded by some dense shell, the hotspot's emitting neutrons. These neutrons come out at about 14 mega electron volts of energy. So these are the primary neutrons from the DT fusion reaction. Now, neutrons are notorious for not interacting with matter as well. However, there is a small chance that they will collide with some of the matter in the surrounding shell. And when they do that, they scatter and lose some energy. So they'll lose some of their 14 MeV energy, and they'll go down into like the 10 to 12 to 8 energy bin. And essentially the amount of scattered neutrons we see divided by the amount of primary neutrons we see is proportional to how much density is surrounding the shell. So that gives us a diagnostic. So if we can measure these 2 quantities simultaneously, we can constrain what the areal density is. And the way we do that is with a magnetic recoil spectrometer, and it's regularly used at the NIF to measure areal density. The way this diagnostic works is a little technical, but essentially what happens is the neutrons from the implosion fly out of the experiment. They interact with a foil that's held some distance away from the target. The neutrons have some probability to hit this foil, and they make deuterons, or an isotope of hydrogen. These charged particles then fly into a magnet, and charged particles in the magnetic field will bend. So the different energy particles will bend different amounts. And we have an array of detectors at the different bending angles. And this is what gives us energy resolution to the diagnostic. So fundamentally, what we measure is essentially the number of deuterons as a function of the deuteron energy. And then we can reconvert this into a neutron spectrum using some using our knowledge of the probability neutrons have to interact with the foil. And so this diagnostic has been hugely successful both on NIF and Omega. And essentially it's been used from the start, and it's followed all of the high performance DT campaigns. And in addition to measuring ROR, it's also an independent measure of the neutron yields, and it's crucial for verifying performance. So as I was on the title slide, I kind of have these number of, this plot we've been showing before, which is kind of the progress we've made in making fusion reactions as a function of year. And what I want to highlight and state is that MRS, this diagnostic, the magnetic recoil spectrometer, provided the best yield measurements for this record shot, and the only ROR measurement we had. And the reason for that is the yields were so high, actually, the other diagnostics in the chamber were kind of set too low in sensitivity, and so they all kind of saturated. And so we almost missed some crucial data just because the performance, the igniting plasma kind of ran away from us in some sense. But MRS was critical in quantifying the performance of that implosion and helping us understand what happened in that experiment. And then the last thing I'll discuss, and then Neil will take over, is kind of some of the X-ray imaging measurements I've been a part of. So so this is how we diagnose the size and shape of the hotspot after we compress it. So ICF hotspots are so hot that they emit X-rays, and we use these X-rays to image the implosion with some apertures. So again, we have our favorite hotspot surrounded by some dense fuel. We can field a tungsten aperture array that will filter out some of the X-rays, but through these little, let's say 100 micron pinholes, the X-rays will pass through and we can image the hotspot on a detector plane some distance away. And what we can do is use those images to look at the shape and size of the hotspot. So here I'm showing you an image of, it's a false color image, but an image of a hotspot. And often we find that in these experiments, hotspots are pancaked, flat, or sausage-like in shape, depending upon the different degradation of the experiment. And that can result from a variety of things like laser drive asymmetry. Was the capsule asymmetric? Was the system in the target chamber offset by a small amount? There's also laser plasma interactions, and just these kind of measurements can help us quantify the different degradation effects. And just for reference, typically a hotspot at the Omega laser facility might be like 20 microns. I think the human hair is around 70 microns. So these are a little bit smaller than that, and width of one of your hairs, which is always interesting to reference. But so this is a diagnostic I've helped helped work on. And one of the things we're pursuing is a 3D image of this of the experiment, of the hotspot as it's formed. And one of the diagnostics we're pursuing is essentially having 3 lines of sight on the chamber. And to do that, we just need 3 detectors. And from imaging in 3 different lines of sight, we'll be hopeful to reconstruct the 3D shape of this hotspot, of what we're assembling. All right, so I'll turn it over to Neil now.
All right, yeah, so I'm going to talk here about a diagnostic we've been developing for measuring the plasma temperature at the University of Rochester Omega laser facility, as Patrick talked about. So the way this diagnostic works is that we're actually going to measure X-ray histories and then use those X-ray emission histories to infer information about the plasma temperature as a function of time. And so what we do is we'll use stepped aluminum filtering that I'm showing in the image on the left. And so the X-rays will have to go through different thicknesses of aluminum before they hit our scintillator array. And we use the individual scintillators behind different thicknesses of aluminum because these scintillators can give us very high time resolution when they encode the information about the incoming X-rays. So the incoming X-rays will be filtered by the aluminum, losing different amounts of the lower energy X-rays before they are then absorbed in the scintillators. And this gives us sensitivity to slightly different X-ray energies in each channel. So we essentially then measure, in this example, 6 different X-ray emission histories in slightly different energy bands. Which we can then use to get information about the time-resolved X-ray spectrum, which is related to the plasma temperature. And on the right here, I'm showing how this light starts out in a scintillator array in the middle of the target chamber, but then must be, the light from the scintillators must be ported out of the back of our diagnostic down a light relay to a camera, which we keep in a shielded location. And this is important because there's a lot of neutrons, as we've talked about, that come out of these implosions. Those neutrons will fly through all of the target chamber walls and everything, and eventually hit your camera and mess up your measurement if you're not careful about making sure you shield that camera from that environment. So we want to measure our scintillator light emission, not direct neutrons from the implosion, which we measure with other diagnostics. We can go to the next one. Oh, I think that was backwards. There we go. Yep. So how would this diagnostic work? Well, what I'm showing here is in this plot is a synthetic data study that we did to kind of confirm the design work that we did on the implosion. So we took simulated ICF implosion, and we took out the simulated X-ray emission as a function of time and energy. I developed a synthetic diagnostic, which we then used to get what the X-ray emission history shown in blue would look like as measured by this diagnostic we're designing. From those X-ray emission histories, we could get the synthetic temperature data, which is shown in the red data points with estimated error bars. And we see that those data points are in line with the initial hydrodynamic simulation, which is shown in the red curve. And so this indicates that in our study, this diagnostic technique will work well for measuring the time-resolved plasma temperature in these implosions. And beyond just this synthetic data study, we've also tested this diagnostic in a prototype design that uses 4 channels and an existing diagnostics infrastructure. So at this point, we've shown this diagnostic works both in synthetic studies as well as in real data that we've collected. And we're looking at options going forward to build this diagnostic at the Omega Laser facility as a permanent and regularly used a new capability there, which may eventually also be of interest for the National Ignition Facility. Go to the next one. So now we're going to kind of switch paces. Instead of going into detail about these diagnostics, just going to throw up a slide here showing many of the other diagnostics that MIT has been involved or has been the primary developer of. Of course, we talked about some of these in more detail, like the MRS, but beyond the neutron spectrum that MRS captures, we also have diagnostics that make measurement of the nuclear emission histories, as well as information about charged particle spectra and charged particle imaging. And we'll point out that we're working heavily on a time-resolved version of the MRS diagnostic called MRST, which will be very important going forward, as having a time-resolved measurement of that neutron spectrum will give us a lot more detailed information about how well the implosion is performing and what we can do to make it better. Jump to the next one. Yep, and so also on that Omega laser facility at the University of Rochester, we develop a lot of diagnostics for that facility. A lot of time, the idea is that we can take these diagnostics to the NIF eventually, but also many of them are dedicated to work that we can do specifically at this laser facility. Similar types of diagnostics, though, focusing on charged particle spectrometers, charged particle imaging, as well as nuclear emission history diagnostics and X-ray emission history diagnostics as well that we've done at Omega. Now I'll point out that all of these diagnostics are developed and calibrated on our linear accelerator facility, which is here on MIT's campus as part of the Plasma Science and Fusion Center. This accelerator is fundamental to all of this work, as at the National Ignition Facility, one experiment can cost $1 million, or at the Omega Laser Facility, $100,000. And so when we take a diagnostic there, you kind of need it to work the first time, because you don't want to waste all that taxpayer money with a diagnostic that doesn't work. So our laser facility here at MIT allows us to test and calibrate our diagnostics so that we can take them to Omega and the NIF with confidence that they're going to work when we need them to. And so in this slide, I'm showing a picture with our accelerator's target chamber of some former and current students, postdocs, and scientists in our group. We'd like to get an updated version of this picture so we could show you all the current faces. But unfortunately, we haven't all been in the lab at one time since COVID has started. Also, normally we would invite everybody over for a tour right after this talk, but unfortunately that's not possible right now either. But maybe in the not too distant future, we can open up the lab for a tour and show everybody how we do this work here at MIT.